Let's work through how to solve a linear programming problem. The question says find the maximum and minimum values of the function and the values of x and y where they occur. So this top function, f equals 5x plus 36y, is called our objective function. This is the function that we are trying to minimize or maximize. And in this case, we are trying to do both. All of these inequalities are called constraints. So these are values which our solution must satisfy. The two down here at the bottom are called non-negativity constraints, and they restrict our solution area to the first quadrant. So to solve a linear programming problem, the first thing we're going to do is graph each one of our inequalities individually. So I'm going to start with 7x plus 5y equals 27. So I'm going to graph this. I'm going to make a t-table, but I'm going to use the x and y intercepts to graph. So one time I'm going to let x be equal to 0 and I'll solve for y. The other time I'm going to let y be equal to 0 and solve for x. So if I let x be equal to 0, and I can just cover it up, I'm going to be left with 5y equals 27. Okay? So divide both sides by 5. Y is equal to 27 over 5. If I let y be equal to 0, I'm left with 7x equals 27. So divide both sides by 7, and I get x is equal to 27 over 7. I'm also going to go ahead and graph my second line, or at least make the t-table for it. The reason for this is I want to know how big to make my graph, like what kind of markings or what kind of numbers I need to go to on my x and y axis there in the first quadrant. So I'm going to go ahead and find the x-intercept and y-intercept of my second equation as well. So I'm going to let x be equal to 0 once, y be equal to 0 a second time. When x is equal to 0, I have 7y equals 21. Divide both sides by 7, and y is equal to 3. When y is equal to 0, I'm left with 5y equals 21. Divide both sides by 5, and I'm left with 21 over 5. So if I convert the fractions to decimals, this is 4.2. This one is 5 point something, and this one is 3.85. And I do that just so I can kind of see where I need to go on my graph. So none of my x or y intercepts are bigger than 6. So if I want to graph this, I can actually just go to 6 on each axis. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So my first graph has the ordered pair 0 and 5 something. So I'm going to put a dot right there in between the 5 and the 6 marks. And then my x value, I have 3.85, so not quite 4. And I'm going to connect the dots. I'm also going to label these values because most likely these will be some of my corner points. So this was 0 and 27 over 5, and this one was 27 over 7 and 0. So next, for my first line, I need to see where all of the solutions are that make this inequality true. So I'm going to test a point on either side of the line. An easy point to test is 0, 0. So I'm going to plug that into my first inequality. When I plug it in, I get 0 is less than or equal to 27, which is a true statement. So I'm going to shade the side of the line that has 0, 0. So right there under the shaded portion, that's all of the places that make my first inequality true. I'm going to do the same thing for my second line. I'm going to go and I'm going to graph the line. So 0 and 3 is one ordered pair. And then 21 over 5 and 0. 21 over 5 is roughly equivalent to 4.2. So a little bit past the 4 hashtag. And connect the dots. This is my second line. Again, I'm going to test to see on which side of this orange line I have ordered pairs that make this inequality true. So again, I'm going to test 0, 0. So plug this into my second inequality. 5x plus 7y is less than or equal to 21. So 5 times 0 plus 7 times 0 is less than or equal to 21. I'm running out of room there. 0 is less than or equal to 21. This is true, so shade the side of the line that has 0, 0. Alright, so I had 4 inequalities total, but these 2 inequalities at the bottom, like I said, restricted our solution to the first quadrant. Now, our solution region, or our feasible region, is the overlap of the 2 other shaded regions. So this section right here. So this is our feasible region. It's called bounded. I could draw a circle around it and encompass the entire thing. So bounded just means that it's enclosed on all sides. Next, we need to find the corner points. The corner points give us our minimums and maximum value for our objective function. So we'll find the corner points. So down here we have one. Corner points are the places where our inequalities meet. This is the intersection of x equals 0 and y equals 0. So the value 0, 0. This one, which I forgot to label, is the y-intercept for the orange line. That was 0, 3. This one is the x-intercept for the purple line, which we already have is 27 over 7 and 0. And the last one is the intersection of 7x plus 5y equals 27 and 5x plus 7y equals 21. Now, one of the things that you can do in your calculator, you have a program that I've installed called Solve System. You probably have less programs than I do. So go to the one that says Solve System and hit Enter. And then it's going to ask you for the coefficients of your 2 equations. So starting with the top equation, we have a coefficient in front of x of 7, in front of b of 5, and a constant of 27. For our second equation, 5, 7, and 21. So it tells us that our lines intersect at the point 3.5 and 0.5. Let's turn those things into fractions. 0.5 is 1/2 and 3.5 is 7/2. Because this is a terminating decimal, you could actually do that in your calculator. So 3.5 is equivalent to 7/2. If you don't have the Solve System program in your calculator, you can always use substitution or elimination to find the ordered pair that these 2 things have in common. Alright, the final step in solving this linear programming problem is to take those corner points that we found that were made by our constraints. So our corner points were 0, 3, 0, 0, 27 over 0 and 0, 27 over 7 and 0, and 7/2 and 1/2, and plug them into our objective function. So we're looking for minimums and maximum values of our objective functions, and they occur at the corner points of our feasible region. So plug these things in. 5 times 0 plus 36 times 3. So plug this in. It's going to be equal to 108. Now plug in your next corner point. That one was easy. Plug in your third corner point. So 5 times 27 halves. This is equal to 135 over 7, or 19.29. And then finally, plug in your last corner point. Oh, I messed up. These are supposed to be 36s, aren't they? That's okay, thank goodness. They were both being multiplied by 0, so that didn't matter. We don't have to go back and recalculate. But we got it on that last one. 5 times 7 halves plus 36 times 1 half is equal to 71 over 2, or 35.5. So we were asked to find the minimum and maximum value for our feasible region. Our maximum number over here on the side looks like 108, and this occurs at the corner point 0, 3. And then we have a minimum value of 0 at the corner point 0, 0. So we have solutions to the linear programming problem. A function value of 0 when x equals 0 and y equals 0. A maximum function value of 108 when x equals 0 and y is equal to 3.